Okay, 8.6, exponential and logarithmic functions. They're graphs and they're models. Again, if you see the word model or application, you know there's going to be some word problems in here. These are real life word problems though, so hopefully you won't hate them as much as like Billy who goes to the store to buy 24 watermelons. So exponential functions are the ones we're going to start with. If it has the word function attached to it, you know it's going to pass the vertical line test. So an exponential function will have a base, that is a b, and the base has to be greater than 0, but it cannot be equal to 1. The reason for that is because if you have a base of 1, think about what happens when you take 1 times 1, nothing changes. You take 1 times 1 times 1, nothing changes. So we have to put that little indicator in there that b cannot be 1. But b can be a fraction as long as it's positive. So there's 3 different graphs given. There's one where it says f of x equals 2 to the x. This one is 1/2 to the x, and this one is 10 to the x. So for an exponential function, you have your exponent is where your variable lives. That's what makes it special. So I cannot have an exponential function like this. This is not an exponential function. That's a quadratic. That's what we talked about in 8.5. So that's different. The exponential function has the number in the base, and then it has your variable in the exponent. And if you are in business, you want to see exponential functions in your growth in sales and in your profits. Because what happens is it starts shooting off really, really, really fast, and that's what you want to see. This one, not so much. That's an exponential decay where you start really high and you start crashing. This is what you don't want to see in your business because this is not good. This one's even better. You'll notice that how much sharper and steeper it is, and that's because the base was larger. This had a base of 10. So the higher your base number, the steeper your incline. If you have a fractional base number, then you have a decline like this. And so that's generally what you're going to need to know in order to match your graphs on your Pearson. If it has a fractional base, you know it's going to be a decay or a decline. If you have a large base, it's going to be a massive growth. And that'll help you, honestly, with 90% of your graph problems, just knowing those 2 pieces of information. But there is a lot of other good information about these graphs. The graph will always contain the point 0, 1. Unless it has been translated or moved, simply because any base raised to the 0th power is equal to 1. So the y-intercept is 0, 1 here, 0, 1 here, and it's 0, 1 here, because none of these have been shifted horizontally or vertically, and so they all cross at the exact same point. Number 2 is stating exactly what I said, where if the base is larger than 1, then you have an increasing graph. If the base is between 0 and 1, you have a decreasing graph. There is what's known as a horizontal asymptote at our x-axis. So we haven't talked about asymptotes yet. But an asymptote, if you look at this graph, notice it doesn't just immediately dip down below the x-axis. And that's because you have an asymptote here. And an asymptote is a boundary line. An asymptote is where your graph is going to hug, basically. If you want it to stick in your head, you want to remember it. A lot of people, when in movies, when things start going bad, they say either kiss your ass goodbye or hug your ass goodbye. You're going to hug your asymptotes here, always. And so, can you cross a horizontal asymptote? You can, but in this class you won't. With these, you will not. So if I kept drawing these graphs out, it would get really, 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 really close to my x-axis, but it would never actually cross or touch, ever. Same thing for these. Even if they're declining, it's going to hug, 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 and it's never going to cross. So that's something that's interesting. It will help you to identify a graph if you have one that shoots off down here way below. The domain for these, that is all of your x values, is negative infinity to positive infinity. These shoot off upwards and outwards. There's not an x value that will never be hit. And as long as these have not been moved up or down, then your range, which is your y value, will be 0 to positive infinity. Again, because if we never cross our x-axis, we can't get down here to these negative values for our y's, is how that's going to work. There are some special exponentials known as your natural base exponentials. These are the exponential functions that have a base of e. On most of your calculators, regardless of which kind you have, this one is not an approved calculator, but it has this e here next to the pi. E is an irrational number, and we use it in math, kind of like we use pi. On this calculator, which is an approved calculator, you will see that right here above the ln button is this e to the x. That's where your e button is. And if you don't know where your e button is or how to use it, I can show you after class. But e is just a number, and if we have e as our base, then we know this as our natural base exponentials. There's nothing really all that important about that, except that later on when we go to solve some of our exponentials, we are going to use ln, which is the natural log, over the regular logarithm based on what our base is. So lots of information about graphs. We're not going to do any of the graphing because you're going to just pick out of multiple options on the Pearson site. We're going to jump straight into some word problems, some compound interest problems, and work those because these are actually exponential problems that are real life, really applicable to your lives. Even if you're not a business person, you're going to deal with interest. Either you have student loans and you're racking up interest, or you have a savings account and you're racking up positive interest that way. So the compound interest formula is where you have a certain amount of dollars that either you are investing or you are borrowing. That is known as your principal. And you invest it or you borrow it at an annual interest rate. And it is represented as a percentage. And we have to convert it into a decimal in order to mathematically play with it. And you'll see that as we move through these examples. Then it's going to tell you how many times it's compounded in a year. So maybe it's compounded quarterly. That means it's going to be compounded 4 times a year. Maybe it's compounded monthly to where it's compounded 12 times a year. It will tell you how many times it's compounded. And then it will tell you how many years, or it will tell you how much you've accrued or accumulated. So A is your accumulated total, T is the number of years. For these problems, you will always be given every piece of information except for one. And that one piece of information is what you're going to solve for. So sometimes they're going to ask you for how many years does it take for you to get up to $10,000. So you'll have the $10,000, but you won't have the T, and we will learn how to solve this to figure out what T is. Well, a lot of times you'll know everything that's on the right-hand side, and it becomes a plug and chug where you just type it all in, and you get how much money you either owe or you've made. So this right here, if you are making your note card, is something I would put on my note card because I need to know this in order to do my problems. And so I need to have that either memorized or ready to use when it comes to the test. So flip over. And I know this first one says applying compound interest formula. So above that, I'm going to go ahead and rewrite that formula just so I have it because I know it was on the other side. The annual accrued is our principal times 1 plus our rate over the number of times we compound it, raised to the number of times we compound it, times the time. So suppose that $1,000 is invested at an annual rate of 2% compounded quarterly, or 4 times a year. Find the total amount in the account after 10 years if no withdrawals are ever made. So in any of these problems where I'm given lots of pieces of information, I usually make a list. So I know that I have $1,000 that's invested. That's my principal. It says at an annual rate of 2%. So the rate is 2%. Now I have to change that into a decimal. How do we change a percentage into a decimal? Okay. Which way? Yeah. So you can divide it by 100. You can also just move the decimal to the left 2 places. So right now, if I wrote the decimal, I'd write it right after my 2. So if I wanted to move this into decimal format, I'd go 1, 2, and I'd plot it there, which means I would have 0.02, like this. And the way I know if it's correct is if I move my decimal to the right 2 places, I get back to just my whole number. And I always, just on habit, put a 0 in front of my decimal so that I don't accidentally drop it somewhere. If I am dealing with a percentage of 10%, let's say, just so I can show you what I mean, and I write it like this, there's nothing wrong with that. But if I'm going too fast, I'm more likely to forget about that decimal and then change it to 10, and then it messes up my problem. So I always put a placeholder where my whole number should be, just so I remember where my decimal actually lives. It draws my attention. That's up to you. That's just a preference on you. The next piece of information we have says it's compounded quarterly. So the number of times you compound your money, that is the N. So my N in this case is 4. And then I keep reading, and it says how much after 10 years. So T is 10. So the only piece of information I don't have, or what I'm trying to figure out, is how much money do I accrue. So the A is what I'm missing. So I'm going to plug everything in. I have 1,000 times 1 plus 0.02 all over 4 raised to the 4 times 10. Now, you can do some of it on your paper if you so choose, or you're more than welcome to just go straight to your calculator and type it in. I'm going to go straight to my calculator. Again, this is not an approved calculator, but it gives a nice screen, so I like it. It's the same kind of screen as the blue and white one. I just don't have that one. And when you have to do raised to, you will either have, you don't see that, you don't see anything. You will either have some kind of an exponential button like this one, X to the little box, or if you have a calculator like this little caret. That's what we call this little symbol, this little triangle symbol. That means that if I wanted to do 2 squared, I do 2 caret 2. I don't know if you can, there it is. And that would give me 2 squared. All right, can you actually see that? A little bit, okay. So I have my 1,000, parenthesis, 1 plus 0.02 divided by 4, close my parenthesis, I'm going to go up into my exponents, and then I can handle that 4 times 10 is 40, so I'm going to type in 40. And I hit enter, and I get $1,220.79. I'm going to put my approximation symbol. That's a squiggly equal sign because I did do some rounding. Again, Pearson will always tell you how many places to round to. Typically with money, they're going to have you round to either the nearest dollar or the nearest cent. So here's something that's kind of a sad realization. This is more like a savings account. And this person left their money in their savings account for 10 years, and they made a whopping $220. That kind of sucks. Now, if we were doing like student loans, this would be like every month you accrue $220 because the interest rates are way higher for those. But that's a whole nother topic. So, when they give you everything but how much money you either make or owe at the end, it's a plug and chug. You plug in all the pieces and then you chug them out. Are there questions on this one? All right. There's another form of interest known as the continuously compounding interest. If you are investing money, this is what you want to see. You want something that compounds continuously because every second it's accruing more and more and more money. That's what it's doing. Before, this is only accruing every 4 times a year or every month, depending on what it says in your problem. But when you do continuously compounding, you're getting money like you're building faster is what's happening. And you'll notice that this one is a pretty similar equation really to this one up here. It's just here we had to take into account how many times a year we were multiplying our money. When we are continuously compounding, we don't do that because we are compounding continuously. So we have a base of E. That's the number E that I was telling you about. So you take your principal times E and raise that to your rate times time. This one's known as PERT. That's what I call it because that's what it says. PERT is a nice equation. One, because it's relatively simple. Two, it sounds like a word, so usually it sticks in your head. And then three, later on we will see that our decaying and our growth equations are pretty much PERT. And so you don't have to relearn a whole bunch of equations. We get to use the same one, just in a slightly different format. So let's look at PERT. Suppose that $5,000 is invested. All right, I'm going to make my list. P equals $5,000 at an annual rate of 2.5%. 2.5%. And then I'm going to change that to a decimal by bumping to the left 2 spots. 0.025. Compounded continuously, so I'm going to use PERT. Find the total amount in the account after 4 years if no withdrawals are made. So my T is going to be 4. And we're not missing anything because we have the E to compound continuously. We have all of our bits and pieces except for our A, which is what we're going to find. Our A equals our principal times E raised to our rate times our time. And we are going to plug it in. 5,000. I don't need that. And then my E button, exponent button, 0.025 times 4. Approximately $5,525.85. So in 4 years, this account gained a little bit over $500. Granted, there was more invested and the interest rate was slightly higher, but the fact that we are compounding continuously helps our money to grow faster. Questions on either of these interest problems?
How do you check that into
the other one? All right, what can you see? There we go. So for this one, I would do 5,000, and then I have my E, so I'd have to hit second, E to the X. Notice it puts a parenthesis, which is good because I need that. So I put 0.025 times 4, and then I have to close that parenthesis and hit enter. Did that help?
Yeah.
Cool. If you have an even more basic one than that, sometimes you have to do the E part first and then do the times 5,000 part last. Again, I'm more than welcome to walk anybody through that as well. I just don't have one of those up here. Other questions? Okay. Let's throw in exponential growth and decay in here for a minute. Now this function looks a little bit different, and that's mostly just because these values are not dealing with money. Usually these are dealing with people. We'll see exponential growth and decay in populations. And so usually this stands for how much the initial population is. And so instead of having P here, we have A sub 0. The A sub 0 is the amount or the number present at time 0. So it's what we're starting with. The population in China in the year 2000, maybe we want to examine the growth from 2000 to 2024. And so 2000 is our starting point. And so that's going to be our A sub 0. And then we have this K to the T up here. K is either going to be positive, and thus we have exponential growth, or K will be negative, and we have exponential decay. This is our PERT, though. Sure, we have a sub 0 and k, but what we have is we have our principal, our starting amount, times the e, times our rate, times our time. It's the exact same thing. So even if you don't memorize the a sub 0 and the k's and things like that, we're going to be working with the same information using the same formula. It's just instead of money, we're going to talk about people or bacteria or something like that. Same process, though, which I think is really nice. Let's keep things simple. So we will do a exponential growth and decay problem here in just a little bit. I have some word problems at the end. We have carbon dating, doubling time, and then growth of population. But let's talk about, we talked about exponentials. And just as a refresher, just for a second, our exponential graphs look like this. They don't cross the x-axis. They either shoot up to the right or they fall down to the right. Depends on if it's an exponential growth or an exponential decay. Okay? The reason why I want to point that out is because there's an inverse or opposite of exponential, and it's a logarithm. So if you skip down and look at this logarithm graph for a minute, you'll see it's actually doing kind of the opposite. Yeah, we're still going to grow, or we're going to fall, but look what we're doing. We're hugging the y-axis this time instead of our x-axis. It's flipped. That's what makes them different. It's like we took our exponentials and we shifted them on their side and we get our logarithms. So a logarithmic function, again, has a base of b. It has to be positive and it cannot be 1. That's the same stipulations we had for our exponentials. So we have, sorry, I know I skipped from the top part. We have this logarithm of b equals x, where x is greater than 0. And x can be 1 here. It's just not very interesting. But what we're going to use to help us solve logarithmic equations is we're going to use its connection with exponentials. If we have an exponential function, like b to the y equals x, we can write that as log base b of x equals y. You will hear me say it a lot today, where the base becomes the base and the answer becomes the exponent. So what that means is if I have my logarithm, here's my really general one, and I cannot type this in. One thing you'll find is on your calculator, you have a log button, you have an ln button. The log here has a base of 10, so that means your b is 10. The log here with ln means you have a base of e, that number e. So if you have log of anything besides e and 10, your calculator cannot do it. Plain and simple. If I have y equals log base 2 of 3, I can't type that in. I don't care what calculator you have, you cannot type that in. So we have to understand how to go back and forth between logarithms and our exponentials so that we can actually compute this information. So how do we do that? Well, if I'm going to use my base becomes a base and my answer becomes the exponent, what I'm going to do is I'm going to take the base of my logarithm, that's this little number down here, and that becomes the base of my exponential. So 2 would be my base. The answer becomes my exponent. The answer of our logarithmic equation becomes my exponent and my exponential. And what I was taking the log of becomes my new answer. Now, while this isn't necessarily a nice one because I literally just made it up on the fly, we could figure out the algebra behind it to solve and figure out what y is. We can do this. We can't type this in anywhere. So we have to be able to go back and forth. The base becomes the base and the answer becomes your exponent. That's what we're going to work on. We're going to do a couple of those at the end as well. And I think just to kind of save some time and get to the actual problems, I'm not going to go through all the characteristics of the graph. You can see what they are. They're great. They're good information. but you do need to be able to look at these graphs and say, okay, if I have a swoosh that goes like this or like this, it's going to be a logarithm. If I have swooshes that go up like this that hug my x-axis or down like this, I have an exponential. Hopefully the exponential ones kind of stick with you because maybe you understand exponential growth or decay in terms of market value or what you want to see your business do in terms of thriving. A little extra tidbit in case you do continue on in any type of math class. Exponential and logarithmic functions are known as inverses of each other. And what that means is you can flip-flop the x's and the y values from your exponential graphs, and you can graph your logarithmic graphs. That's actually what you would do in order to graph them. Because again, we can't type in most of our information into a calculator for logarithms and get out information back. And so we use our exponentials a lot to help us represent our logarithmic information. It's more user-friendly. And so we use it a lot. All right, let's flip over. Let's do some problems. As I mentioned when we were looking at the calculators just a minute ago, we have what's known as our natural logarithms and our common logarithms. Our natural logarithms correlate with our natural exponentials. They have a base of e. So log base e of x, we usually shorten that to ln, which is natural log. The natural log of x. That's why you have an ln button on your calculator. Because again, I can't type in log base e into my calculator without my ln. You will use your ln button a lot more than you'll use your log button in this class. The common log is where you have a base of 10. That's your actual log button that's on your calculator. It's assuming a base of 10, and because we assume a base of 10, we oftentimes will just write it without a base at all. So if you see a problem and there is no base given, the base is 10. It's kind of like when we write out x plus 2. This is the same thing as saying 1x plus 2, but to keep things short and sweet and simple, we don't typically write our 1. It's the same thing. It's just a common way of writing our math. We like to keep it as short as possible and as uncongested as possible. So ln of x means you have a base of e. Log of x means you have a base of 10. If it's neither of those, it will tell you the actual bases. It'll be log base 4 of 18 or something like that. It will give you everything else. Okay, let's do our application problem so that we can see what's going to happen here. And we can actually use all of this information. Because honestly, just getting a bunch of information is fine, but it doesn't really tell you how to use it. And so let's learn how to use it. We are going to find the time for an amount to double. So this is another interest problem, but it's slightly different. It says, suppose that a certain amount, P, is invested at an annual rate of 1.5% compounded continuously. How long will it take for that amount to double? If we are compounded continuously, which equation are we going to be using? PERT. That's exactly right. We have A equals P-E-R-T. PERT. Now, they don't give me my principal. It's just P. That's kind of what we're trying to figure out somewhat. We don't know what it is. We know the rate is 1.5%. And we know that it's compounded continuously, so we have the E. How long will it take for it to double? So the T is what we're actually looking for. But we also don't get P. So let me just ask a general question. If we start with P as the amount of money that we're investing, and we're trying to get it to double, what are we trying to get it to do? Like, A is how much it is at the end. So what would A equal if we're trying to get our money to double? Double a P, how would we write that? Yeah, 2P. 2P. So we actually have, even though we kind of still have two variables looking like they're still going to live here, we have enough information to start working this problem. Because instead of writing A, I'm going to write 2P. And you're going to see what happens here in just a second. So I have 2P as my A, P as my P, E, my rate is 0.015 times my T. The T is what I'm actually looking for. And I know I have a P, but notice I have a P on both sides of my equation. So just in general, if I was trying to get this P on the right over to the other side, what would I do? Yeah, we divide by P. But if I divide this side by P, I have to divide this side by P. But what's P divided by P? 1. So notice our P's go away. We have 2 equals e to the 0.015 t. Now we have one variable. For your doubling time, or if it's a halving time or tripling time, it will always happen like that, where your principal, which is usually unknown, is going to go away. So here's what we need to do. We need to solve this and figure out what t is. Okay, so here's kind of a little rule. I'm going to go back up to the top to write the rule down, just so that there's room for it. When you're doing a problem like this where you have an exponential, let me just show you. You have an exponential right here. We're going to use logarithms to actually help us solve it. If the base of your exponential is equal to 10, can you see this? Yes. Then what you're going to do is you're going to log both sides. If the base is 10, log both sides. If your base does not equal 10, so if it's any other number, including e, then you're going to ln both sides. So, like I said, 90, 95, 99% of the time you're going to use ln, because very rarely will your base be 10. And that's the only time you can use the log. So if the base is 10, log both sides. If the base is not 10, you're going to ln both sides. For this exponential, our base is e. That's not 10, so we're going to ln both sides. That means I'll have ln of 2 equals ln of e raised to the 0.015 t. And here's another special rule and why we like lning, especially with e's. Ln of e raised to the k is just k. The ln e part will go away. So that means I'm going to have ln of 2 equal to 0.015 t. And if I'm trying to solve for t, what am I going to do? Well, we have ln of 2 equals 0.015 t. So I'm trying to get t by itself. Yeah, we got to divide. I'm going to divide both sides by that 0.015. So I'll have ln of 2 divided by 0.015 equals t. Now, maybe you were already typing in ln of 2. One thing I would recommend with all of these problems is doing the work on your paper and typing it in at the end for the word problems and things, because what happens when we start using logs and natural logs is there's a lot of rounding. And if you round early in the problem and then round again and round again and round again, you get further and further away from the true actual value. If we wait until the very end to type it all in, then we have a more accurate answer. And so at this point, I would type it in. And I'll use this calculator. So I'm going to take ln of 2, and since it's on top, I'm going to actually put all that in parentheses just to be on the safe side. I use lots of parentheses if I have any question on what it's going to classify. And I get My t is approximately, what are we going to round to? Let's say 2 decimal places. 46.21. So here's a sad notion. If you are investing a given amount of money, you don't have to know how much money. Whatever amount of money, and you have a 1.5% interest rate, which is not very good, it's going to take you 46 years to double your money. If you invest $500, it will take you 46 years to get to $1,000 because of how slowly we start accruing everything. That's what that just says. That sucks. But we can mathematically find it. So that's good. So the big things here are once you get to your exponential like this, if the base is 10, you'll log both sides. If the base is e, you're going to, or anything else besides 10, you're going to ln both sides. And then this special rule right here, where if you ln e raised to whatever the exponent is, you can drop the ln of e and just look at the exponent, which helps us then to solve and finish out. Questions on this one? All right, let's look at that population one that I was talking about earlier. Bless you. It says, according to the data from the United Nations Department of Economics and Social Affairs Population Division, the World Population Forecast for 2020 through 2025 can be projected by this function model right there. So that's a weird function, but they have figured it out. Where x is the year. That's kind of the big part right there. None of the rest of this really mattered. We need this piece of information, and we need x is the year. Those are the two pieces you need to know. So based on this function, based on this model, what would the world population be in 2030? 2030 is what our x would be, because x is the year. So all we're going to do is we're going to type that function with 2030 inside of it. So it'll be f of 2030 instead of f of x equals 2049.73 e to the 0.007506 times 2030. I'll go ahead and warn you, we get some weird big numbers in these problems. All right, let's see what this looks like. 2049.73 e to the 0.007506 times 2030. Yep, big O number. 8494148,538, comma, comma, comma. So in 2030, based on that model, we should have almost 8.5 billion people on Earth. That's a lot of people. So step A, just plug and chug. Step B is a little bit different because it's not plugging and chugging. We do have to do a little bit more algebra. It says, based on this model, in what year, so we're not going to know the year, in what year would the world population reach 9 billion people? The 9 billion people is what we get. We don't know what the year is. So that's our f of x. So for B, we have 9, 1, 2, 3, 1, 2, 3, 1, 2, 3. 9 billion equals 2049.73 e to the 0.007506x. Because we're trying to get to 9 billion. We know it will happen after 2030 because 2030 we had almost 8.5 billion people, so it's going to have to be later than that at least. Now, regardless of how big and weird these numbers are, this problem is really no different than the one we just did where we doubled our investment. Because up here, we had 2p and the p's canceled, then we had a number equal to e. Well, we almost have that here. We almost have a number equal to e. But we have this 2,049 and a bit right here in front. So if I'm trying to get e by itself, I'd have to divide it all. Now, don't use your calculator yet. This is where we're going to write it all out. We'd have 9 billion divided by the 2049.73 equals the e to the 0.007506x. The reason why I don't want to go ahead and type it in is because it's going to give me a decimal, it's going to do some rounding, and I don't want to round until the very last step. Now we have our exponential by itself, and at this point we either log or ln, depending on our base. What would we do since our base is e? We're going to ln both sides. That's exactly right. And what happens when we ln e? It goes away. So I'm going to do that all in one step. But I'll write the little rule over here again. ln e of k equals just k. That's our special little rule. It's just going to save me writing all this multiple times. So I'm going to ln my 9 billion divided by the 2049.73. And all of that's going to equal to 0.007506x. So we ln to both sides, but then the ln of the e, those go away, leaving me with just my exponent. Really close to having x by itself now. What would I do? Divide it all again. Lots of dividing. Because if I divide over here by this, that goes away, and then I divide everything on this side. And I will use the pink calculator to show you how we type that bad boy in. So I have a big old honking thing on top. So ln 9, 1, 2, 3, 1, 2, 3, 1, 2, 3. Divide that by 2049.73. Close my parenthesis, and that closes my ln, which is my top. Divide that by 0.007506. And I find that x is 2037.707, and there's more to it, but I'm going to stop at that point. So it asked me, in what year would the world population reach 9 billion? It's going to happen during the year 2037, but we're going to be over halfway through it. So we're going to say by at least 2038. We're going to round up. Because by 2037, if we round down, we're not there. We're going to be just under 9 billion people. But by 2038, we will be at 9 billion plus some change of people. So while it may look weird to write everything out, you're going to get the most accurate answer by doing it that way and not rounding a whole bunch of times. Are there questions on either doubling time or how we did this population problem? Okay, we've only got one more word problem and then 4 really short just conversion problems. Carbon dating. You might actually do this a little bit in chemistry or a biology class. Or maybe your ambition in life is to be an archaeologist or an anthropologist. All right. Carbon-14 is a radioactive form of carbon that is found in all living plants and animals. So after a plant or an animal dies, the radiocarbon disintegrates. It means it starts getting less. And scientists have determined the age of the remains by comparing the amount of carbon-14 that's still present and the amount found in a living plant or animal. The amount of carbon-14 present after X amount of years is modeled by this exponential function. And it says where A sub 0 represents the initial amount of carbon-14. And then we've got this negative exponent up here because it's a decay. The carbon is getting less and less and less every year. And the X is how many years it's been dead. So it says, what is the half-life of carbon-14? If we are thinking of the half-life, what happens to our A sub 0? The initial amount of carbon does what? Yeah, it gets cut in half. This is kind of the opposite of our doubling one that we did earlier. Our doubling one, we took our principal and then we wanted to see how many years it would take us to double that amount because it was growing. This one is dying. It's decaying. And so what's going to happen is we're going to have 1/2 of our original starting amount, whatever that may be. And so I'm going to do the same process that I did with my doubling one, but this time I'm halving it. So f of x is 1/2 a sub 0. And that equals my a sub 0 e to the negative 0 point. There's 3 zeros after that. 1216x. And just like with our principal problem, notice we have an a sub 0 on both sides. So if I try to group those together, they end up going away because I would divide both sides by a sub 0, meaning they go away. So I would have 1/2 equals e to the negative blah, 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 blah. So I have my exponential by itself. So what do I do next? Yep, I'm going to ln both sides. So I would have ln of 1/2 equals the ln of e to the negative 0.123, 1216x. But the ln of e, that's going to go away, leaving me with just the negative 0.123, 1216x. So if I'm solving for x, what do? Divide it all by that negative stuff. Because then that would cancel over here. And I would have x all by itself. So we're going to take ln of 1/2, divide that by negative 0.123, 1216.
Are we leaving 1/2 in a fraction the whole time, or are we just putting 0.5?
It doesn't matter.
Okay.
I put 1/2 as a fraction, but you could put it as 0.5. It should compute out the exact same way. So we find that the half-life of carbon-14 is approximately 5,700 years. So it takes 5,700 years for me to get half as much carbon. Part B says if the initial sample contains 1 gram of carbon-14, how much will be left after 10,000 years? This one literally is just a plug and chug because the 1 gram is our a sub 0. The 10,000 years would be our x. So for B, we're finding f of 10,000. We're plugging in 10,000 in place of our x. So I would have 1 in place of my a sub 0, but that seems a little bit redundant, so I'm not really going to type that in. Or write that. I'm going to have e to the negative 0.123, 1216 times 10,000. And we can do a simple type in. We don't have to do any other work. We don't have to ln both sides. We don't have to do anything. We just type it in. So I'm going to do e to the negative 0.123, 1216 times 10, 1, 2, 3. That doesn't seem right.
That's how much would be left.
Oh yeah, that does seem right then. Thank you. Get me back on track. Let's round to, I think in your homework it has you round to 4 decimal places, so we'll round to 4. So we started with 1 gram. After 10,000 years, we're down to about 1/4 of a gram. That's a long time. I don't want to do the same experiment for 10,000 years, but. So half-life, your starting amount gets cut in half. Doubling time, that's where you're doubling your amount. You could potentially see tripling times and things like that, but I think usually they stick with doubling and halving. So these last 4 are just converting. That's all we're doing. This goes back to the definition of our logarithms. If it gives it to you as an exponential, they want you to write it as a logarithm. If they give it to you as a logarithm, they want you to write it as an exponential. So this is the base becomes the base, the answer becomes the exponent. Now, that's easier going from logarithms to exponentials. So I'm actually going to start down here with these 2, because then I can kind of talk my way around it for the others to show you what I mean. But the base becomes the base, the answer becomes the exponent, is when we go from logarithms to exponentials. So the base of my logarithm for this one is 2. That will become the base of my exponential. The base becomes the base. The answer of my logarithm becomes the exponent of my exponential. And what I was taking the log of becomes my new answer. Now, in all of these cases, they're all numbers. You can actually check. You can type 2 to the 5th power into your calculator. You're going to get 32. It does work. Sometimes one of these is a variable, and we actually do end up solving for it, just not today. So the base became the base, the answer became the exponent. What we were taking the log of becomes our new answer. So what would D look like? 4 to the 3rd power equals 64. The base became my base, the answer became my exponent, and then what I was taking the log of becomes my answer. Now, when we go the other way, we're still using the same rule and the same logic, it's just kind of backwards. So I know I'm going to have an answer, and I have my log, I have my base, and I have what I'm taking the log of. Those are the 3 pieces I kind of have to fill in. Well, the base of my log is the base of my exponent. So my base is 4. The base becomes the base. The answer of my logarithm became my exponent. So that means this is a 2 over here, and what I was taking the log of becomes my answer. So I still use the same thing, and oftentimes I will write this information over to the side, so I can just kind of fill it in, and you can check it. So the base becomes the base, the answer became the exponent. So how would I write 1/10 to the negative 4 equals 10,000 in logarithmic form? Like, what is the base of my log? Yeah, because that's the base of my exponential. So log of 1/10 of what? 10,000 equals what? Negative 4. The base becomes the base. The answer becomes the exponent. What I was taking the log of became my new answer.